Hello, I'm Alex, and I'm here to present our paper NAC-TCN, Enhancing Temporal Convolutional Networks with Dilated Neighborhood Attention for Emotion Understanding. First, let me talk a little bit about our motivation for this research. First, we understand that emotions are a critical task in many domains, and that these emotions are very complex and don't happen over a single time plane. In fact, commonly, they will happen over a long time frame, which is where recurrent structures come in, such as RNNs and LSTMs, and these have been enhanced with attention variance. This comes with also a set of challenges among the benefits. Some of these specifically are issues with balancing memory and performance, issues with attention mechanisms, and training stability. First, a little bit of background on some related work. First, on LSTMs and RNNs. We all know that RNNs and LSTMs take in an input and produce a hidden state, and that hidden state is passed into the next cell, creating a recurrent structure with an infinite receptive field. The only thing limiting this receptive field is memory cost and the idea of vanishing exploding gradients, which can be an issue with very long sequences, which make it ineffective at times. In comes the TCN, or the Temporal Convolutional Network, which relies on dilated causal convolutions in order to create a similar network that can have sequential data, but instead relies on convolutions. And this creates many benefits, such as the ability to compute time steps in parallel, opposed to having to wait for one hidden state to finish being computed from one cell for the next cell. Which is a key difference from the recurrent structure that exists in RNNs and LSTMs. This is a major speed up. One of the main downsides is that the receptive field is no longer infinite, but determined by the dilation factor, the kernel size, along with the number of layers. And some of the limitations of these are compared in this matrix here, where we see GRUs and TCNs both have low memory, but if you add attention to a GRU or an LSTM, we see issues with the amount of memory it uses, but we gain an attention mechanism, and we see in the TCN we do gain more stable training. And the final item on this list is TCAN, which is an attention-based temporal convolutional network that adds an attention to the existing temporal convolutional network to have the benefit of stable training. But this comes at a memory cost. The NAC-TCN, which is our model, aims to address all three of these issues in one comprehensive model. On to the actual architecture. The NAC-TCN architecture can be exhibited in this figure here, and it is very similar in overall structure to a TCN, with three major contributions. First, we introduce the dilated neighbor attention from Hassani and Shi in 2022, which is interspersed within this temporal convolutional network structure in these blocks. We also introduce causality to this dilated neighborhood attention in order to create a causal sliding attention, which is important to maintain the same causal effect of a causal convolution. Finally, we add an enhanced residual connection to NAC-TCN blocks. This residual connection has many benefits. Specifically, it allows for dimension scaling and also keeps ensures that the gradients are alright, even with a network with a very high depth. Onto one of our contributions, which is taking the existing neighborhood attention, specifically the existing dilated neighborhood attention, and making it causal neighborhood attention, which can be also seen as a causal sliding attention. To illustrate how this works, I'm going to illustrate with a kernel size of 3 and a dilation of 1, which is just a normal causal sliding attention with no dilation, just for simplicity. This kernel size actually represents a neighborhood, which can be viewed as the key value space, and we query each of the values in this key value space in order to create an output. As seen in this equation here, we simply use the prior work on attention, except in this specific neighborhood space. And one of the main benefits of using the existing neighborhood attention algorithm is speed up in performance due to the existing CUDA kernels. And we see over time, just like normal dilated neighborhood attention, if you make the key value or kernel or neighborhood space the length of the input, you actually end up with just a global version. In this case, it's a global causal attention, whereas in a normal neighborhood attention would just be attention. Onto an overview of NACTCN block. Specifically, when we talk about interspersing our dilated neighborhood attention, what we mean is instead of having two convolutions after each other, which is normally what happens in a temporal convolutional network, we usually have one convolution for downscaling and one for actually applying the input at that dimensional size that is wanted. Instead, we have the first convolution act as a downsample followed by a dilated neighborhood attention layer, while everything maintains the same structure as before. And we add spatial dropout in order to ensure channel independence, which can add some performance boost. And again, we have that 1x1 convolution. And each block maintains the same dilation and kernel size. So each block actually represents the same thing as one layer in this model. So that is where this becomes this. All right. On to my next point, which is the dilated structure. This dilated structure attempts to make it analogous to a TCN in important ways, specifically maintaining the receptive field and while still having this attention mechanism. And causal neighborhood attention tries to follow the exact same structure as a causal convolution, but note this is not the case for normal neighborhood attention due to how corners are handled. Alright, so why still have convolutions? The main benefit is due to faster training and smaller models. If you have a convolution instead of a attention block, you clearly save some performance cost, and we see that attention overall in some cases will actually tend towards attention will tend towards convolutions based on previous literature. So in the end, really we want to have the best of both worlds, where we don't have so much attention that becomes a detriment actually to the performance, but we still want to have this attention mechanism. So this creates a nice balance. In addition to that, just the logistical side of it, the dimensional scaling and the residual convolution. So convolutions, the reason why we have them is for faster training and smaller models, in addition to logistical issues related to dimensional scaling. Onto the testing methodology. So small and large models sizes are used for evaluation. So how does this large model work? This large model matches the hyperparameters of a TCN model that performed well. And this TCN model, we take all the parameters and we find the analogous versions in our NACTCN, and they all match 1-to-1 in this case. And the large parameter size, there'll be a larger parameter size due to the fact that neighborhood attention performs more operations than just a convolution, but less than normal attention. So this will obviously have a larger size, but it's a reasonable larger size. It's not anything in a large magnitude. And then we have the NACTCN small model, which shows comparable to high performance with a smaller model. And we obviously optimize all the hyperparameters, but we scale them, make sure we scale them down to keep the same receptive field but have a smaller model. And then for our evaluation metrics, we have the coordinates correlation coefficient, where a higher number is better. Then we have AUC ROC for another data set where a higher area is better. And then we finally have our operations or efficiency metric, which is the multiply accumulate operation, which is approximately half flop, so it should be lower. As for the data sets, we use three main data sets for analysis. The first one is AFWILD2, which contains over 1.5 million annotated frames from various YouTube videos. And that uses the valence arousal emotion scale and has cropping provided by the dataset owners in order to give everyone a standardized input. And then the APU dataset also uses valence arousal emotion scale, which is on the right there. It's you can imagine it as a pair of points that represent emotion in two-dimensional space. And there are 600 video clips here. And finally, Emo React, which has over 1,000 videos with 17 emotional states that can happen in a way where you can have multiple emotions happening at once, which creates a multi-class binary problem rather than just a categorical problem. On to our results. The first significant result is comparable performance with fewer parameters with the AFU dataset. As you can see, we had less parameters and some performance. 2 agree with attention, and then if we go to the small model, we also had better, a lower amount of operations with a very similar performance. So we see overall here there's very comparable performance among our common methods, with NACTCN just coming out barely on top. We see more drastic and better results in our other 2 data sets, specifically AFWILD2, which is a larger video data set. We see that we have a significant 4-point advantage over the transformer model, and a 6-point advantage over TCAN and these other structures that we talked about earlier. And we can see also from the number of parameters that it's very enticing to use NRCTCN when you're looking for like a high performance model that is also efficient. And then if we also look to our right, we have the Emo React data set, where we also see significantly better results with also lower parameters and operations. And we performed a few ablation studies as well. Specifically, we find that causality is key. We explain our reasons for why we think this in the paper, but specifically emotions are a causal relationship, so we need to treat it as such in our model. And then the residual connection is important. We see about a 7-point boost when looking at the NACTCN small architecture and removing the residual connection. And for some future work, we would like to explore the poor transfer learning that happens with TCN, which we expect to also exist in NACTCN when it comes to time warps due to how rigid these kinds of structures are. Also, we'd like to test on alternative domains, specifically for the causality, to see if that relation still holds. And finally, we'd like to find improved performance on small datasets such as AFU, where we saw comparable results instead of higher results. We believe this is due to the fact that AFU did have long sequences, so we did have a deep network, but we did not have as much data to train that deep network, which caused issues. All right, thank you for listening. All links are on our website to any information you might want, and you can feel free to contact me by email.